This meeting is being recorded.
In this video, we're going to take a look at sample exercise 9 from chapter 19 on electrochemistry. In the last video, we were able to determine by solving for E cell whether or not we had a spontaneous or non-spontaneous reaction. But we didn't actually assign a numeric value to our delta G. So say we do want to find the actual value, a number to associate with our delta G, we can use this equation shown here that relates that negative NFE cell to delta G. It also relates, when an equation as equilibrium, the equilibrium constant here for a redox reaction, this KEQ. So notice the second form of this equation is negative R, which would be the gas constant of 8.3145 joules per mole Kelvin. If you recall, there's more than one gas constant. This time we're going to talk about it in form of energy. T, our temperature, will be given either in Celsius or Kelvin. You'll need to convert to Kelvin if it's not already there. And then we'll take the natural log of our equilibrium constant. But say we can calculate the value of delta G or KEQ. We can also rearrange this equation as needed. So I'm going to write another form. So once we find our delta G, we can solve for our equilibrium constant. So if I was to rearrange this, I could divide delta G by negative RT, and that would leave me natural log of KEQ. To reverse that natural log or cancel that out and get KEQ by itself, I would take the E of both sides. So my rearranged equation for KEQ would be E to the negative delta G over RT. So we may utilize this later on in this equation. So let's take a look and see if we can first break this into our half reactions. So I'm going to have 3 Mg solid gives me 3 Mg2 plus. All right, so I have my magnesiums balanced. Let's look at our other half reaction. We have 2 Al3 plus gives me 2 aluminum solid. Okay, so everything is balanced so far except for the charge. Let's see, what do we have? So we have 3 times a plus 2, so we have a plus 6 charge over here. I have 0 over here. So I need to add 6 electrons to this side, and this would give me my oxidation half reaction. So magnesium is being oxidized. Aluminum will be reduced by the same note. So I have 2 times plus 3, so I need to add 6 electrons to get this to 0, like the aluminum on the product side here. So I have 6 electrons in, 6 electrons out. So because of that, I don't need to multiply by any coefficients, and now I can just solve my E cell is going to be my E, my potential of my cathode minus my potential at my anode. So I would have gone to my table, grabbed these values. So let's do that real quick. We see for aluminum, we have this down here, the negative 1.66 value. And then I will give you the value for magnesium because this is not on this table. So we have negative 1.66 for our reduction. So that would be at our cathode here, negative 1.66. And then you would have to look up on another table, or you'd be given this information in a question, if it's not in the table, of negative 2.36. So this is my value at my anode for the reduction of magnesium. So what happens here, to solve for E cell, we're going to have negative 1.66 plus 2.36. So we're going to see that our E cell is equal to a positive 0.70 volts. Now, I can solve for delta G by plugging this into my negative N. So that would be 6 moles of electrons. My F was at 96,485 joules per mole volt instead of coulombs. And then I'm going to multiply by 0.70 volts. So this turns out to be a value in joules of negative 405, 237 joules. Now I'm going to take this information and I'm going to plug it into my KEQ equation. And I'm going to convert this to kilojoules first because I want that to cancel out with my gas constant. So I'm going to put that in kilojoules as well. So let's see what this will look like.
This meeting is being recorded.
Okay, so now that we have our values for delta G, since we've already solved for E cell, we're going to plug this into our KEQ equation, and that will simply be E to the negative delta G. So that's a negative. Just to save some space, we'll call this 405.273 kilojoules. And then on the bottom, my R constant, if I take that and plug in 8.3145 times 10 to the negative third kilojoules per mole Kelvin, that will cancel out my Kelvin when I turn my 25 degrees C into 298 K. All right, so now Kelvin will cancel, my kilojoules will cancel, and I'm going to end up with my unitless value for KEQ. If you plug everything in correctly, take the E of your value, you should get something around, for a KEQ, 1 times 10 to the 71st power, and this was derived from approximately 9.9 times 10 to the 70th. So if we round to only 1 sig fig, we can see that this is a very large equilibrium constant, and this would be a spontaneous reaction, so we expect it to be product favored.